Um, so let me introduce myself. My name is Ravi Chityala, and as Satishan said, I work as a senior engineer at a radiation oncology company called Electa. I mostly work on the patient positioning part of Electa's product. And along the way, we formed a team within Electa, and then we have been doing deep learning work for some time. And in the process, we learned all stuff like scikit-learn and Tensorflow and things like that. But along the way, I realized one thing, which was deep learning by itself. If you think about it, there have been architectures that have been already created. You find a lot of papers on these architectures like ResNet and Inception and LeNet and Google LeNet and all that. And people tend to use one of those architecture to do their deep learning prediction. So which means that many a times you don't actually have to come up with your own architecture. You could piggy bank on what's already there. But the biggest chunk of work that you do will actually be in the data preparation process. Because the data that you get, let's say from Kaggle or let's say from somewhere online, it's all cleaned up for you, ready to use, and you just plug it into an architecture and it spits out some stuff for you. That all makes us happy, good, but that's not how real world works. Real world is a lot more complicated. You have to actually sit and spend way more time on cleaning up data, and probably your deep learning will be the last part that might actually be the quickest part, even if it takes a few days to actually run a model. So this talk is essentially about how do you prepare your data, or not exactly how do you prepare your data, more about what are the modules that people tend to use in preparing the data. Okay? Because how do you prepare the data is a very complicated question, because it all depends on your field. Let's say you're in the financial field, your data is mostly tabular format. I'm in the image processing area, so my data is mostly in the matrix form. So which one you use, which one I use is all completely different. So I'm just going to talk about what are the various modules that are there. There are many more modules other than the ones I'm going to talk about, but I'm just going to focus on few, which is the most commonly used one. Okay. I joined Twitter, or I got a Twitter account in 2007, but I didn't use it for 10 years. So I'm trying to revive my Twitter account. So I put my Twitter handle there. So if you become my follower, I just wanted to point out that my Twitter account is @Chityala. For the people who join my Twitter account, I will be posting where I'm going to put all these PowerPoint presentation and notes in Twitter, so that way you get the first access. Because the conference does send you that information later, but if you want first access, then become my Twitter follower. All right, so as Satishan was saying, I co-authored a book with my wife Sridevi Pudipedi. She's right here. This book is on image processing using Python, and it's available. It's published by CRC Press, available at Amazon in case if you're interested. I also teach at UCSC Silicon Valley Extension, which actually turned out to be a good thing for me. It's a blessing for me because I actually ended up learning a better way of teaching things, thanks to teaching to all those folks advanced Python at UCSC. All right, so to the talk. This talk will give an overview of all these modules, and I'll talk about the differences between some of them, where you would use it, and things like that. So we'll start with Numpy, then we'll talk about scipy, OpenCV, Pandas. I'm saying TensorFlow here because I use TensorFlow, but there are also other ones like Theanos, Caffe, and stuff like that. But I'm going to stick to TensorFlow because that's the one I'm familiar with. And finally, I'll end with multiprocessing. Along the way, I'll show you an example, or two examples. One that will use Numpy and Pandas. The other one will use Numpy, OpenCV, and multiprocessing. Okay? So that way you get a sense of how it actually works. Instead of me yapping here forever, I want to actually show you some code example. Okay? Okay. And the multiprocessing is one that people might not think it's a data preparation stage, but I'll show you an example and it'll make sense why you actually should know multiprocessing when it comes to data preparation. Okay. So this is from XKCD. Probably some of you have already seen this. This is simplest definition of how we do deep learning today. Okay. So it's basically throw a bunch of linear algebra at it, throw a bunch of data, and keep stirring the data until the thing actually looks okay. We are still in a very early stage of deep learning because deep learning is pretty new, and the field is going so fast. In my years of experience looking at research papers, I haven't seen a field produce papers at this rate. It's just mind-boggling. You can't even keep up. You can have an RSS feeder to check what are the papers that are being published every day, and you can still not keep up. All the papers that are coming out. It's just amazing. And it's not just from the architecture perspective, how people are using it, what people are thinking about to do in the future. It's very amazing to see that happen, and I'm very happy I'm at least being part of a small chunk of it. Forget about being the big guy. All right. If you're doing deep learning, I would actually recommend you install one of the Python distributions. Okay. So for those of you who may not have heard about Python distributions, these are some commonly used ones: Anaconda, Nthought, Canopy, and Nthought, and Python XY. I have the links right there. The idea behind the distribution is, if you take, let's say, Numpy and scipy, for example, it uses, behind the scene, it uses some C libraries like Boost, C++ library like Boost, and things like that. So many years ago, before distributions were popular, if you wanted to set up Numpy on your computer, you literally have to compile Boost. Along the way, you'll have to compile 10 other libraries, okay? And that's not something easy to do. Even for me, when I was doing it long time back, it was just impossible. It'll take a few days for me to get the whole thing going. And even then, I would never feel confident. Then some smart guys found out there's actually a business opportunity here. They said, okay, why you don't have to waste all your time. I'm going to build all these Boost libraries and everything and create a version of Numpy that is meant for your operating system. And it's going to work just like the way you compiled it. Okay? So that's where these amazing business opportunities came, and Anaconda, Nthought, and Python XY is an open source version of it. Anaconda and Nthought both have a free version. Most people could just use the free version, you'll be fine. But if you find that there's a paid version gives you more, you are welcome to buy one of their paid version as well. Okay. So let's start with the first module. So the reason I'm pointing out Python distribution is so many of these distributions, they are written specifically, they've been prepared specifically for scientific computing purpose. So they automatically come with Numpy and scipy, which are the two pretty standard computing libraries that you need. Anaconda, for example, they have a very clever and a very smart way of doing virtual environment, where they virtualized it so well that you can actually have multiple versions of Python under the same one Python distribution. So you can use Python 2.7, and you can switch your environment to Conda environment to 3.5, and you can switch to 3.6 if you want, and you can use all versions using one installation. So Numpy and scipy comes in ready. If you have Conda environment, for example, installing Pandas and all that is just super easy. It's already easy, but they made it even more easy. The same is true for Nthought as well. Nthought is not as cool as Anaconda, but it does similar things. Okay. And just to point out, Anaconda was actually the CEO of the company is the guy who wrote Numpy. Okay. Yeah. That's because Python is single-threaded. But I'll talk about multiprocessing later, where how you can parallelize your code so that you can actually do more in the same amount. So these distributions are compiled for a specific operating system and assuming a certain architecture. Yeah. Yes, they have been compiled for so that everybody can use it. But if you want more performant code, then you have to take care of the thing. Yes, exactly. Yeah. So these have been created so that everybody can use it. But if you want more performance, then you'll have to do your own compilation. For example, when you install TensorFlow right out of pip install, it'll warn you that, let's say you're using an Intel processor, it'll tell you that your TensorFlow is not optimized for SSE, SSE compiler set. Okay, but if you compile it yourself, then the compiler will take care of fixing that for you. Okay. All right. So the first one you're going to talk about is Numpy. Numpy is the core numerical computing library in Python. It does all the linear algebra things like finding transformations, inverse, addition, subtraction, multiplication, all that very, very basic stuff. Okay. It was originally created by Travis Oliphant, who is also the CEO of Continuum Analytics that produces Anaconda. And you can find more details at numpy.org. Okay. I'll walk through slides and then I'll show you an example and show you where it's actually being used. The next one I want to talk about is Pandas. Pandas is a data manipulation visualization library. This was actually created by Wes McKinney. He was working for a financial firm. He created it because there was a need that they had to process lots of data, and he wanted a really high-performant library. So you might be wondering, why not use Numpy? There's actually a difference. Financial data are tabular data. Most of our computational data is matrix data. Even though they look like two-dimensional, but there is actually a significant difference between the two. If, let's say, for example, I take an image, and if let's say there are m columns and n rows, I cannot arbitrarily move one of the column to another position, right? Because that means that my image I'm modifying my image. It no longer makes any sense. But if you think about a tabular data, let's say that contains age, name, etc., etc., it doesn't matter whether the age comes in the first column, age comes in the third column, it means exactly the same thing. Okay? So even though the two might look like a two-dimensional data, tabular data are space variant, which means you can move them around in the column wise and they will still make sense. But matrices, on the other hand, they are space invariant. You're not supposed to move them, because if you move them, you're changing the meaning of the data. Okay? So that's where it kind of differs. So Pandas comes in handy for the data where your columns can actually move around. So which means it's not necessarily only for financial data, but any data that can be put in a tabular form, and that where each column is independent of the second column, Pandas actually works out perfectly well for you. Pandas provides two data structures, series and data frame. A series is a one-dimensional data structure, and data frame is a two-dimensional data structure. Pandas also was written with one thing specific in mind, which was being able to read large amount of data. So you can have a CSV file that's 100 gigabytes in size, and you can say, I want to only get information from column 1, column 5, and column 10, even if it has like 10,000 columns. Okay, you can specify what are the columns you actually are interested in. Whereas in the case of Numpy, you're literally reading the whole thing. If you read an image, you're reading the whole image. It also provides tools for data visualization, because it was created in an environment where they wanted to analyze fast, visualize fast, and keep moving forward. And so it has lots of visualization tools already built in. And you can find details in pandas.pydata.org. Okay, so let's go to this example. During the TensorFlow workshop that we gave over on Friday, I did bring this particular example. So some of you were there, probably will find this the same. But for the rest of you, this might seem new. Okay, so here is a Jupyter notebook where I'm actually going to do linear regression. Okay, a really simple linear regression. I'm going to take this data that's from this archive.ics.uci.edu, AutoMPG data. Essentially, it's a CSV file. It's an Excel file that contains information about different cars. What's their miles per gallon? What's the model? What's the make? How many cylinders? How much is the cylinder displacement? And things like that. Okay. So it's got a lot of data. But I'm interested in only two of them. I'm going to do a linear regression fit between the displacement, the cylinder displacement, and miles per gallon. We already know that if the cylinder displacement increases, your miles per gallon will go down, because that means the cylinder is bigger and bigger, and your miles per gallon will go down because your cylinder is big. It needs more fuel, and generally, big cylinder means it's in a big vehicle doing lots of stuff, so you're going to have a lower miles per gallon. Okay, so that's the analysis we want to do. So I'm going to read the CSV data, and Pandas makes it super easy. You don't have to open a file, you don't have to close a file. You just say pd.read_CSV, and you feed a CSV file, boom, it's done. Okay? You get this data frame. So this is the data structure which Pandas uses to store the data, because it's a tabular data. And I'm only interested in two columns. And to get the information about one of those columns, you just can do it just like the way you do a Python dictionary. AutoMPG is the name of the data frame, and the particular column is displacement. Okay, so you get one data from only one column of data from that, and that data is actually an integer. But I want to convert it to float because I'm going to do some linear regression. I don't want to lose precision, so I'm just going to convert it into float. And this as type float is a Pandas method. Similarly, I'm going to read the MPG data. MPG column, convert it into float. Now I have the displacement and the miles per gallon, both. Then I'm going to apply simple transformation. I want my data to be approximately the same range, because if your ranges are way off, you could result in numerical instability. So I'm going to keep my numbers in reasonable range. So I'm going to divide all rows in each of those columns by 100. So the numbers are a little bit smaller and my numerical stability is guaranteed. So I'm going to do it by saying dot apply. I'm giving a lambda function. You can give a regular Python function as well, where this lambda function is basically saying take every item in the column and divide it by 100. Okay? And I'm going to do the same thing for the miles per gallon as well. So both data is now in narrow range. This is the cool thing about Pandas. Pandas was created with an environment where they wanted things to happen fast. So if you want to look up basic statistics on the data, you don't have to actually write too much code. You can just say auto mpg underscore disp dot describe, and it'll describe what the data is. For example, it gives you information about how many items are there, what's the mean value, what's the standard deviation, min, 25%, 50%, etc. So that's a quick way to see whether the data is actually in proper shape. Because again, remember, preparing the data is the biggest part. And preparing the data means you first have to feel confident the data is actually even useful. Because many a time the data might not actually be useful. Or the data might be just contain a lot of stuff that's wrong. So you want to check whether there's something wrong with the data. And the describe is the fastest way to check whether the data is actually in some reasonable number. Okay, so then I'm going to go ahead and set some hyperparameters like learning rate, epochs, and display step, and all that. In the case of TensorFlow, it takes NumPy arrays. When you feed, you have to feed NumPy arrays. So I'm going to take my auto mpg underscore disp, which is a data frame, Pandas data frame, Pandas data series, and convert it into a NumPy array, and then feed it to my TensorFlow graph. And to do that, it's very easy. You just say np.asArray, you give it the data frame, and NumPy will convert that into a NumPy array. NumPy array of, it's essentially a vector, even though it's called NumPy array. Okay. So I'm going to go ahead and run this as well. Okay, so the next step is, in the case of deep learning, you give batches of data. It's a hard concept to explain at this moment. But just remember that this yield is a keyword that tells in Python. It basically allows you to return stuff from a function, and you actually can go back into the function again with all the previous state of the function being preserved. Okay, it's a very powerful concept. This is the concept that actually allows the possibility of doing iterable objects in Python. And I would actually recommend, in case if you're already not familiar with it, actually look into what this actually does. Okay. If you talk to experts in Python, they will say that you should always use yield keyword to do your work, which is actually true. But there is this one scenario, especially in deep learning, where I would say yield keyword is literally mandatory. Okay? Because you're going to prepare batches of data, and the batches of data are going to come out of a function, and the best way to get data out of a function and go back into the function is the yield keyword. Okay? So no longer think of yield as an optional feature that you should learn about in Python, but if you're doing deep learning, think of it like a mandatory feature that you should learn. Okay? Because if you pick up any examples online, you will find people using yield keyword to actually fetch batches of data. Okay? All right, so then I'm going to specify the x and the y, which are the data that I'm going to feed into my TensorFlow graph. But I have to specify a placeholder, because in TensorFlow, everything is a graph, and everything is essentially like an abstraction. You don't actually do the computation immediately. You always do it lazy, which means you build the graph, and at a later point of time, you call session.run, and you say, here is the data. I want to use this data to process this graph. Okay. So these x and the y are the placeholders, and at a later point, we will then feed this train underscore x and train underscore y into this placeholder uppercase x and uppercase y. Okay. So it's going to happen later. And these are my weights and biases. Essentially, this is imagine this is just a line fit. So it's essentially like y equal to mx plus b. And this m is nothing but the w in this case. And the b is the intercept in the linear fit. And b is the bias in the case of linear regression. And then, as the cartoon was saying, you throw in a bunch of linear algebra now. That's what we are going to do here. We're going to throw a bunch of linear algebra. We're going to say that the predicted value is nothing but x times w plus b. We are essentially saying y equal to mx plus b. That's a predicted value. And then you also have to specify a cost function. Essentially, how well am I doing is the question. So how well somebody is doing, that will be nothing but the predicted value minus the actual value square divided by whatever normalization factor you want to put in. Okay? And that's what we are doing here. Predicted minus the actual, you're raising to a power, and then dividing by the number of samples, and however you sum it or make square roots or whatever factor you want to use, you could use it. But essentially that's the cost function, at least in this example. Then this is all the cool parts of TensorFlow. You don't have to worry about optimization and all that. You just say, I want a gradient descent optimizer. Here's the learning rate for it. And here's a cost function over which you have to optimize. Okay. So at this point, we have defined basically a graph that ends at optimizer but goes all the way up to the prediction. So it goes like all the way here. All right. Then I go ahead and run. When I run, I'm going to get batches of data using the yield keyword. So which means in the first iteration of the loop, I'm going to get one batch of data. And if you remember, this yield had two things. One was, it returns a tuple, and the tuple, the first item in the tuple is x, batch of x values, and the corresponding batch of y values. Okay. So I said the batch size is 30. So that means I'm going to take 30 rows from my CSV file, and I'm going to return 30 numbers in x and 30 numbers for y. So those 30 numbers will be stored in x, stored in y, and then I'm going to then feed it to the session.run. At this point, when I say feed dict equal to x colon x, comma y colon y, and at this point is when the graph actually gets computed. Okay. And I'm going to get the cost value, and the cost value comes back. Oh, cost value is being stored, but I'm not doing anything with it. But at every 100th epoch or so, I print out what my status is, how bad my cost function is. And if I run this code, maybe I should run everything. So my cost started at 0.139, and then it's been subsequently decreasing, and it keeps decreasing. So if, let's say, there is other functionalities like, let's say your cost function keeps decreasing and then it starts increasing again, that means there is something wrong with the parameters, or maybe the model itself is wrong. Maybe you're trying to fit something that doesn't actually fit. You're trying to put a square peg into a round hole. Maybe it won't work. Okay. So that's all an evaluation that you have to do as you learn deep learning. And in this case, it's smooth. It's a simple example, so it's always going to be nice and clean. And we end up with the final W and the final B. Okay. There is also this functionality called TensorBoard built into TensorFlow that allows you to visualize this cost function, maybe all other things that you want to visualize. Okay. All right. Any question about this? So essentially this example talks about, let me just finish this. So this example basically talks about two things, which is Numpy and Pandas. It just gives you a quick overview. Again, there's a lot more details to Numpy and Pandas, but at least it gives you a sense of what it can and cannot do. Yeah.
Yeah. So you mentioned it was more advanced or whatever, but in get batch you did a random. You got a random number in there, and I'm not sure what
Okay.
you're doing with it. Like
Sure.
sample your.
Okay. So there is different ways to sample the data and get a batch of data. Okay. So I'm following one approach, which is. So let's say I give the x-val and the y-val input here is your full data set. Okay, the train underscore x and the train underscore y. That contains 398 rows. Okay, I feed that data. Now, initially the count is 0. And when it comes here, 0 less than array length divided by batch size. Array length was 398 and the batch size is 30. Okay, and that's approximately 32. So this number is 32. Is 32 greater than 0? It is true. So it's going to go ahead and generate a random number that's between 0 and 398 minus 30 minus 1. Okay? And then I'm saying, go get all the values from, let's say it's 100. Okay? I'm saying xval ran start colon ran start plus batch size. That means I'm saying get all the values from row 100 to 100 plus 30. Okay? And similarly, the same for y, the corresponding value for y. And I'm making a tuple out of it, and then I'm returning it back through the yield keyword. Okay? And with the yield, what happens is when you come back, when you come out of the function, and then you go back into the function again, you'll be back at the same point, and the next possible line it can execute is the while. Okay? With yield, when you go back, it remembers all the previous state. So that means it remembers xval, yval, array length, batch size. It remembers count as well. Okay, now count is 1 because it remembers the previous state was 1. So is this statement still true? Yes, it is still true. 32 is still greater than 1. Okay, and so you're going to return a different starting point and return a bunch of values. Okay.
But won't your xval, your return to xval and yval change its size each time? Like since you're
No,
generating
this is what determines how big it's going to be.
oh, it's the index.
Yeah, it's the index being randomly, a starting point that's randomly generated. But after that, I'm only getting 30 number of values and returning it back. So this is one way of sampling. The other way of sampling is you can say, I'm going to always do 0 to 30, 31 to 60, etc. And then you can say, then after the next epoch, I can say 1 to 31, 32, etc. So the different ways of sampling. This is one way of doing it. But no matter what method you use, you will eventually be using the yield keyword because it saves a lot of memory. Okay. Yeah. What method?
Actually using the random positions underneath the kind of order.
I don't know whether it'll prevent overfitting, but it's more like making sure that you don't give the same set of data for as batches. For example, if I always do 0 to 30, always do 30 to 60, 31 to 60, every epoch I'm giving only that, that means it's only learning in one order. Okay. By doing this, I'm making the order a little bit shuffled. So I can feel like, okay, it might actually learn better. Okay. Probably it'll prevent overfitting, but there are other ways to prevent overfitting as well. Okay. So right. So the next one we're going to talk about is combination of scipy, OpenCV, and multiprocessing. Okay. So scipy is a scientific computing library. What's the difference between that and Numpy? Numpy contains all the basic linear algebra commands. Scipy builds on top of it because not every one of us want to implement FFT in our library. Okay, we just want to use something that's already implemented, that's somebody who's very smart, make sure that it's all optimized and ready to go. So scipy was essentially created with that in mind. So you will find things like fast Fourier transform, you will find a lot of image processing stuff, you'll find a lot of signal processing, and that's just the starter. There is just so many going on in scipy. And then there is also this, this experimental arm of scipy, the scikit world, where they put all kinds of interesting algorithms, like scikit images there, contains lots of useful image processing functionalities. Although it's still considered experimental, people just use it. And then the other famous one is scikit-learn, which is pretty powerful. In few lines of code, you can actually get machine learning done. Okay. TensorFlow is verbose, but scikit-learn is a lot more concise. Yeah. Yes. Yes. But it's easy for people to just get started with machine learning, get a sense of what it does and how machine learning works. But it's not necessarily performant. TensorFlow is much more performant. But TensorFlow also tends to be more verbose. And you also have to learn some philosophy behind it. Scikit-learn, on the other hand, is like you can pick and figure out from looking at few examples, you will understand what it's doing. So you can find more details at scipy.org. Okay. So the next one is OpenCV. OpenCV is another amazing library. It's just impossible to describe its usefulness because some of the things you think are so hard to do, they will just say, call this one function. Okay. And internally that function does some amazing magic and you just call and you're done. So it contains lots of image processing and computer vision algorithm, and definitely that's a good library to use. And they also have a C++ and the Python interface. So there's another useful thing about OpenCV. So if you're writing a code in Python just for testing purpose and you want to port it into C++, then if you use OpenCV, then you can just call the corresponding C++ function, and you'll do it, and it'll look exactly the same because its underlying code is exactly the same. Okay. The last module that we'll talk about is multiprocessing. It allows spawning of one or more processes. This is different from multi-threading. In the sense you'll literally be starting multiple Python processes. So when I run this code, when I run the example that I'm going to show you, I will open my activity monitor, and you can see that there will be suddenly 4 processes of Python started. Okay. So why would that be useful? Because your computer probably has 4 cores, or maybe 8 cores, or maybe 16. I don't know how many cores your computer might have, but you can use all the cores. So, and multiprocessing is only few lines of code. You just sprinkle few lines here and there, and suddenly your code runs 8 times faster because you are starting 8 processes. Okay. And these processes can actually communicate with each other. Although in this example I'm not, but realistically speaking they can. You can check out more details in this multiprocessing library, this URL. Okay. So the next example we are going to see is for lung segmentation. Okay. This is a lot of code, but really it's not all my code. So there is this, I don't know how many of you are familiar with Kaggle? You are? Okay, good. So Kaggle announces competitions regularly, and some of them are worth a lot of money. Like for example, this data science bowl was like $1 million prize. Okay. Essentially, somebody spent a lot of time doing all this data cleanup for you, and then they said, okay, here is the data. I want you to predict something, okay, or I want you to classify something. That's not the useful part of Kaggle. The other useful part, which I find, you can get the data from the data tab in every competition. But the other useful part is the kernels. Okay. So these kernels mostly contain Jupyter notebooks, like the one I was demoed previously. But they contain a lot of useful things that people have done. For example, in this case, it's a lung cancer detection. This is a part of the Data Science Bowl 2017. So this guy spent time, what's his name, Guido Zuidhoff. So he spent time analyzing the data, and he has all these stuff he wrote for Jupyter Notebook. This is actually useful for people who are not in the medical imaging world, because CT images, unlike photographs, every pixel value actually has a meaning. In photograph, pixel values don't have meaning, because depending on the brightness of the room, even a light-skinned guy could look dark if the room is dark. Okay, but in the case of CT images, if a number says 1,000, that means it's a bone. It's guaranteed. There's no way it's wrong. Okay, assuming it's all calibrated, and hospitals will calibrate their machines. So these kind of nuances about medical imaging that people who are not in medical imaging don't know, you will find people explaining all these stuff in the kernel. Okay. For example, air is -1,000, kidney is 30. So if there's a pixel value of 30, it's probably a kidney tissue. Okay? And there might be a pixel with value of 30, but in the area of kidney, everywhere where there is 30, it's guaranteed it's going to be like the kidney tissue. So he's explaining all these stuff. And you will find lots of these kernels that do wonderful work. Some of them are incomplete, but many of them are actually very, very useful, where people have to spend time visualizing the data. Maybe they even tell you what is the best way to process this data and things like that. So don't just stop at the data section. Go to the kernels also. And if possible, go to the discussions also. All these are pretty useful. Okay, so this data science bowl, as I said, is for lung cancer detection. And from one of the kernels, which I referenced here, I took most of the code. Okay, but the problem with this code was it was running in one process, and I was trying to process my images, and it took like 24 hours. Okay, but I had a 8-core machine in my office, so why can't I make it faster? So that's where I wrote the multiprocessing version of it. Okay. So most of this code is exactly from this part, from this URL, until approximately here. This I modified a little bit. The last function I modified a little bit, but until that point, it's pretty much the same. Then comes the multiprocessing part. So now, to make, there is lots of data. So if I set it to run for 24 hours, you guys have to wait for 24 hours, and that's not possible. So I took a very small section of the data, actually only one folder with 4 images, and then I copied it 4 times to simulate the condition of processing 4 folders of data, and each folder containing 4 images. Right? So these are the 4 folders. They contain exactly the same image, except the folders have different names. Okay. Now, okay. What this does is, maybe I should first show you the output. That way it will be easy. Maybe not this one. Okay. Okay. So, by looking at these two, you would immediately guess what I'm actually segmenting. So, I'm segmenting all the area where there is this. Okay. So, this is approximately the lung area. So, he's trying to segment that. So that's the work that guy did. Now I have to run this across like I think it was something like 30 gigabytes of data, and it was taking 24 hours. So now instead of running it on a single process, I modified the code so that it can run. It can take one folder. So I'll start one process and hand over one folder to that process and say go do the work. So that means if I start 4 processes, that means I'm processing 4 folders at one time. Okay. And if I have, even if I have like 4,000 of them, that means I'll be done in 1,000 steps instead of 4,000 steps in a single process. Okay, so that segmentation process is what I'm doing here. I'm calling the previously written functions like load scan, get pixels HU, and all that stuff. And then I'm building a mask where I'm going to put all my masks, which is the segmented images. And then I'm asking it to do the separate underscore lung, which is the one that actually does the segmentation. And finally, I'm writing the mask out using OpenCV. All right. Okay. So and I have a place where I'm going to start running my code. I specify the input folder, the output folder, and if the output folder doesn't exist, I'm going to go ahead and create it. I'm getting a list of patients. Each folder is one patient. Okay, so I'm going to get a list of all the patients. And I'm going to sort it. There's no need for it, but I'm going to sort it. Then I'm going to start a time, start the time before I do the calculation, and I'm going to check the time, the duration for the calculation. Right? And currently, I commented both the serial version and the parallel version. So I'm going to go ahead and uncomment the serial version. Okay. Before I do that, I want to open my activity monitor. Yeah, I will. It's okay. A little more. Okay. From the back, it might be difficult to see, but let's see. So there are 2 Python processes running right now. There's a one Python 2.7 process, and there's a Python 3.6. Okay. So I'm going to go ahead and run this code. Oops. Ah. No such file address. Oh, I'm in the wrong direction. Python long.py. There you go. So I'm running a serial version of this code. And the serial version for those 4 images, if I process them serially, for those 4 folders, it will take approximately like 150 seconds. Okay. So while you're waiting, let me go ahead and explain the multiprocessing version. Okay. The parallel version sounds a little more complicated, but essentially it's not that complicated. Okay. It's more line of code, but it's not that many. You first import the multiprocessing module. Okay, I could have done it at the top, but I'm doing it here just so that I can highlight it clearly. I'm going to get the number of cores on this machine. Okay. And for that, multiprocessing provides a function called CPU underscore count. Apparently, the CPU underscore count is not a very reliable measure of number of cores on a machine, but it works on a Mac, so I'm using it. But if it turns out that you already know how many processors are there, you can just hard code that number here. Like for example, here the point where I've highlighted, number of cores, you can just put 4 here if you already know your machine has 4 cores. So we're going to create a pool of processes. To create a pool of process, you just say multiprocessing.pool, and you say how many processes you want to start. In this case, my number of cores is 4, so it's going to start 4 processes. Now, once I start the pool, I'm going to call my function and tell, okay, the first process, use this folder. Second process, use that folder, etc. So that's the next step I have to do. And for that, I'm going to use pool.apply async, and I specify the function that needs to be called, which is segment image, which is same as this call. Okay? And I have to supply the arguments to that function. And how am I supplying the arguments? Maybe I should wrap this. I'm providing the input folder, I'm providing the output folder, which is a pretty standard constant values. I'm also specifying a patient, which means the folder name for one of the patients. Okay? And I have to go through all the patients. So for that, I'm doing the for loop here. So it's essentially a list comprehension that builds a list of apply asyncs. Okay? So which means this apply async is going to be called 4 times. The first time, it will be called to the first folder's name. Second time, it will be called to the second folder's name. Third time, third folder name. Fourth time, fourth folder name. Okay. Once you're done with that, you close the pool. You have to call join. These are boilerplate code that you have to add. And if you do want to get some output back, you have to say r.get. In my case, I'm not interested, but I'm just showing it to you here. But sometimes you want to get some output back from the function, the segment underscore image. In my case, my segment image is going to write to a file and it's done. There is nothing I'm getting back from the function. Okay? In case if you do want to get, then you have to call r.get. Okay? So let's look at the output. So it took approximately 142 seconds to run this. Okay? Now I can run this code in 1/4 of the time. Yes, I will. Thank you. Okay. So I'm going to now run the parallel version of the code. The calling is pretty simple, the same as the previous one. And the whole thing will run in approximately 40 seconds. Okay. So which means I just got a 4 times speed up on a laptop. Imagine how much you can get from a desktop with 32 cores. You can go from weeks of processing to just maybe a day of processing. I guess I should have come up with some joke for this 30 seconds I have to wait here. Does anybody have a joke or a question? Either one is fine. Okay.
If we use a GPU version of Tensorflow?
No, here we are processing the data. We are not yet doing deep learning. We're not doing deep learning yet. Yes, if you're doing deep learning, using a machine that has GPU capabilities will definitely make a huge difference. And I have seen easy speedups. With no code change in TensorFlow, you just take the same code, run it on CPU, move it to AWS, run it there. Suddenly you see like 4 or 5 times speed up. No code change in TensorFlow. But we are still in the pre-TensorFlow stage. So that's why we have to do multiprocessing ourselves. Yeah. Now in this case, I'm doing CPU only. CPU only. But considering my computer has so many cores, I could as well start as many processes as I want and make my things go fast. Okay? But if the code is such that, let's say not this libraries, but let's say there is some other library that has both CPU and GPU built in, and if it can do data processing, then just using a GPU machine will be more efficient. Yes, it could be. It could be. It again depends on the case. In some cases, data processing might not be that big. Deep learning might be the most complicated work. In some cases, data processing might be the most. And like in image processing, we generally tend to do more data processing. And deep learning does take time, but data processing also takes a long more time. Because medical images are hard to get. That means you have to do some work to get the data in great shape. So as you can see, the total time taken is 39.40 seconds. And all that you did is, other than adding the boilerplate code, other than adding this boilerplate code and these 2 lines, you only had to add these 2. Build a pool, call apply async and say, here's a function, here are all the inputs, go do the work for me. Okay, yeah.
I have a question. If you were to have four, say you had 4 cores,
Mm-hmm.
and you had 8 processes, they just give you 2 processes in serial.
I think it tries to start all the 8 process. And I think it juggles between the two. I'm not 100% sure about it, but you can try to start 8 process. And it will actually start 8 process. Yeah. Yeah. 4 of them, yeah. So one thing I didn't point out when I was running the code is this. Okay, let me put it a little bit to the side. Okay, I'm going to run it again, but this time I'm going to open activity monitor. Let's go back. We have 2 Pythons running, Python 2.7, Python 3.6. Now when I run, you will suddenly see there is 4 more started. 4 more Python processes started. Okay. So. Yep, that's it. There is some slides on TensorFlow, but we are running out of time, so let's go ahead and for questions. Any questions?
For pre-processing your images, you talked about multiple libraries. Which ones? Like there's OpenCV, there's scikit-image, there's probably just scipy itself. Which ones do you use or find it more valuable? There is nothing like one I find more valuable. If let's say I'm looking for a certain type of transformation and it's only available in OpenCV, I just use OpenCV because I don't want to rewrite the whole thing myself. But if it turns out it's available somewhere else, for example, there are other image processing libraries that are not very popular, not to the amount of OpenCV, things like Mahotas. It does certain things very well and it does very fast. So if it turns out that has it, then I'll just use that. So it's all depends on the problem I'm trying to solve. It's no one simple solution for that. And all of them return you NumPy arrays?
Most of them do return NumPy arrays because they all using NumPy to do the numerical computing. So we are talking about algorithms, but algorithms still need numerical computing. So they all use NumPy arrays because they don't want to recreate them either. So they return back NumPy arrays. Yeah. Any other question? Yeah, here Paul. Paul in the front has a question.
I've seen this tool, Keras, K-E-R-A-S.
Yeah.
Would you recommend that at all?
So Keras is not a data processing tool. It's more for the deep learning process. So TensorFlow is pretty.
This is before.
Yeah. This is before deep learning. So TensorFlow is pretty verbose. You have to type a lot of code to get some amount of work done. Keras was basically built as an abstraction that makes things easy for people who want to use TensorFlow or Theanos or both. So they make you write fewer lines of code, but in turn it goes and calls TensorFlow to do the work. Or you can, Keras is good. Keras is nice. Especially if your architecture is pretty complicated, looking at that corresponding code in TensorFlow is very difficult. Looking at the corresponding one in Keras actually would be make you keep you sane, essentially. TensorFlow code can look a lot more complicated. Yeah. Yeah. To my knowledge, it's only abstracts Theanos and Theano and TensorFlow. I don't know whether it does MXNet and. Oh, okay, it does. Okay. Okay. Yeah, in that sense, yes, it is correct. Exactly. That's another advantage of it. So you don't have to lock yourself to one vendor. You don't have to become only a TensorFlow guy. You can be a Theano guy also. Yeah. Or MXNet, whatever. Or Go. Yeah, sorry. Anything else?
If you're doing something really intensive like perceptual hashing of images, so this is like computing image signatures for image processing, is that generally GPU based? What libraries do you recommend? Or?
Anaconda has a library called Numba, which does something. I never used it, so I don't know all the details behind it, but it does GPU computing. But you have to write some code to make it happen. It's not like the way TensorFlow does, where it automatically does stuff for you.
This one is a little bit of work that you have to do. But again, I'm no expert in that, so maybe I should.
No,
Stop.
I mean, Numba is a generic, it's a generic C compiling math optimizing thing.
Okay.
People do not use it for perceptual hashing. You pick somebody's off-the-shelf C library.
Okay. I'm not familiar with hashing. Sorry.
Yeah,
I'm not familiar with hashing as much.
sure thing.
I don't do that.
Yeah. No, just yeah, it kind of occurred to me. I mean, this is pretty cool, but ultimately, if your pre-processing flow is CPU bound, you're generally going to be compute bound on the pre-processing flow.
Yeah.
Yeah, sure. So I mean, as far as sklearn goes, much of sklearn will never. It's considered mothballed. It will never be ported to GPU, and GPU people are overtaking and rewriting.
Yeah, but sklearn is a
people
good way for people to start off with machine learning. That way, they don't
Yeah.
have to write much code.
But
Eventually, they will. If you're doing deep learning, they eventually have to move to
Yeah.
something bigger, like Keras or Theanos or Tensorflow or one of those.
sure, it's a fantastic paradigm for learning. It's a one-stop shop. All the algorithms and visualizations are included.
And
But-
sometimes people also have simpler problems. Not everybody has complicated problem. If let's say somebody all that they need is to do linear regression or k-mean clustering on really small set of data, yeah, that will just work fine with sklearn, for example. Yeah. For example, the amount of code I showed you for linear regression, probably there will be only like 10 lines of code in sklearn for doing exactly the same work. Feed the data, ask it to learn, it'll learn linear regression with
Yeah,
fewer
and
lines
then-
of code.
Yeah, and then there's like the Intel MKL optimization. So Intel is compiling the optimized LA pack, so you get that as a library. So
Yeah.
that's like a solved problem. Thanks.
Okay. Anybody else? Okay. Thank you so much.